Hi everyone, and welcome to this tutorial. Today, we'll explore the concept of curl, a fascinating topic in vector calculus that has potential applications in physics-inspired machine learning, fluid dynamics, and vector field analysis. By the end of this video, you'll understand what curl is, how to compute it, and its significance in data science and machine learning. To enhance your learning, we've provided Python implementations, examples of curl calculations, a downloadable PDF reference, and additional practice problems with solutions. All these resources are available in the GitHub link provided in the description below. Make sure to check it out as you follow along with the video. Let's dive in. Before diving into our 3D vector field example, let's first take a moment to explore the curl of a 2D vector field. For this, consider a 2D field where the x component is negative y squared plus x, and the y component is x squared minus y. This field creates a diverse rotational behavior across the plane, making it an ideal example for understanding curl. The curl of a 2D vector field is simpler to compute and visualize compared to 3D. In 2D, the curl at any point is a scalar, meaning it is a single value that tells us how strongly the field rotates at that location. The formula for the curl of a 2D vector field is the partial derivative of fy with respect to x, minus the partial derivative of fx with respect to y. In this case, the x component and y component of the vector field represent the two dimensions of the flow. The partial derivatives measure how these components change in space, giving us a way to calculate the curl. For our field, substituting the x component as negative y squared plus x and the y component as x squared minus y, we compute the curl as follows. The partial derivative of the y component, which is x squared minus y, with respect to x, minus the partial derivative of the x component, which is negative y squared plus x, with respect to y. Let's calculate each term. The first term, the partial derivative of x squared minus y with respect to x, gives 2 times x. The second term, the partial derivative of negative y squared plus x with respect to y, gives negative of negative 2 times y, which simplifies to 2 times y. Combining these, the curl becomes 2 times x plus 2 times y. This result means the curl varies linearly across the plane. Positive curl indicates counterclockwise rotation, negative curl indicates clockwise rotation, and zero curl means no rotation at all. In the visualization, you can see the vector field on the left, represented by arrows that indicate the flow direction and magnitude. On the right is the curl color map. Here, the intensity of the colors shows the magnitude of the curl, while the shading distinguishes between positive and negative values. Bright areas indicate stronger curl, while darker or neutral areas suggest weaker curl or no rotation. Take a closer look at the bottom left corner of the field. This region exhibits a strong negative curl, where the field rotates clockwise. Conversely, in the top right corner, you'll notice a strong positive curl, where the field rotates counterclockwise. These patterns align with the flow directions in the vector field, demonstrating how the curl quantifies the rotational intensity of the field at each point. We won't display the Python code for this here, but it's available in the repository linked in the description. I encourage you to experiment with it and observe how modifying the vector field affects the curl. Finally, let's consider how this concept changes in 3 dimensions. In 3 dimensions, the curl becomes a vector field instead of a scalar. This means it not only has a magnitude, describing the strength of rotation, but also a direction, indicating the axis of rotation. In the next section, we'll compute and visualize the curl of a 3-dimensional vector field step by step. Now that we've explored the curl of a 2D vector field and how it represents rotation using a scalar value, let's extend our understanding to 3D. In 3 dimensions, the concept of curl becomes even more powerful. Imagine a field of arrows representing the flow of water, air, or any other physical quantity. The curl at any point in this field measures the local rotation or swirling motion happening around that point. It's like visualizing a whirlpool or a tornado, where the curl quantifies the strength and axis of the rotation. Mathematically, the curl in 3D is defined as the cross product of the del operator, also known as nabla, and the vector field. This operation produces a new vector field that describes the rotational tendencies of the original field. Unlike in 2D, where curl is a scalar, in 3D the curl is itself a vector. The direction of this curl vector indicates the axis of rotation, while its magnitude describes the strength of the rotation. Understanding curl in 3D is essential for applications in physics, machine learning, and more, where analyzing how systems behave in multidimensional spaces is critical. Let's now compute the curl of a 3D vector field step by step, and visualize how its components interact. To compute the curl of a 3D vector field, let's start with a more solid example. Consider a vector field where the x component is y times z, the y component is x times z, and the z component is negative x times y. This field introduces interactions between all three dimensions, creating regions with non-zero curl, making it a great candidate for understanding rotational tendencies in 3D. The formula for the curl in 3D is given as the determinant of a 3x3 matrix. In the first row, we place the unit vectors I, j, and k, representing the x, y, and z directions. In the second row, we place the partial derivative operators with respect to x, y, and z. In the third row, we place the components of the vector field, which in this case are y times z, x times z, and negative x times y. Now, let's expand this determinant step by step. First, we compute the I component of the curl. This involves taking the partial derivative of the z component, negative x times y, with respect to y, and subtracting the partial derivative of the y component, x times z, with respect to z. Next, we calculate the j component, which is the partial derivative of the z component, negative x times y, with respect to x, minus the partial derivative of the x component, y times z, with respect to z. Finally, we compute the k component, which is the partial derivative of the y component, x times z, with respect to x, minus the partial derivative of the x component, y times z, with respect to y. Let's evaluate these terms for our field. The I component involves differentiating negative x times y with respect to y, which gives negative x, and differentiating x times z with respect to z, which gives x. Subtracting these, the I component is negative 2 times x. For the j component, differentiating negative x times y with respect to x gives negative y, and differentiating y times z with respect to z gives y. Subtracting these, the j component is negative 2 times y. Finally, for the k component, differentiating x times z with respect to x gives z, and differentiating y times z with respect to y gives z. Subtracting these, the k component is 0. When we combine all three components, the curl of this field is negative 2 times x in the I direction, negative 2 times y in the j direction, and 0 in the k direction. This gives us a vector field for the curl that varies across space, with different magnitudes and directions depending on the values of x and y. This calculation highlights how curl in 3D works and reveals the rotational tendencies of this vector field. In this case, the field exhibits rotation in the x and y directions, with no rotation in the z direction. If you found this video helpful, please like, share, and subscribe to support the channel and stay updated with more informative and engaging content. Thank you so much for watching, and we'll see you in the next video.